Hi everyone! Today we're starting a new chapter on carbohydrates, and down below you can see some examples of different things that contain carbohydrates or different structures of carbohydrates. So carbohydrates can also be referred to as sugars. And if you've taken biochemistry before, you might already be familiar with carbohydrates. If you haven't, carbohydrates are often referred to in regard to food. So we talk a lot about how many carbs there are in your pasta or what have you. But they can also be found in living organisms like trees. And carbohydrates can provide building blocks that make up the structure of living organisms like trees. Also, carbohydrate derivatives are found in DNA, so carbohydrates are pretty important. Off to the right, I have a couple of different structures for a carbohydrate. So there's an open chain form and then a cyclic form for this carbohydrate. And notice that the carbohydrate has a lot of hydroxy groups or alcohol groups on it. So we'll talk more about that later on. All right, so let's kind of take a step back. Carbohydrates initially were thought to be hydrates of carbon. So for example, glucose, which is a carbohydrate or a sugar, has the formula C6H12O6. And it was thought that this could be written as C6H2O6. So it was thought that there were hydrates attached to the carbons. However, later on, chemists were able to figure out scientists in general were able to figure out the structure of glucose, and they found that it's actually composed of a chain of carbons with hydroxy groups attached, not H2O. But the name for carbohydrates stuck. Now, trees and plants will convert carbon dioxide and water into glucose, this carbohydrate. So let's just write out the formula here. So we've got 6 carbon dioxide molecules and 6 water molecules. And then we're going to use sunlight to convert all of that into our carbohydrate, specifically glucose here. And will also produce 6 oxygen molecules. All right. So this needs a lot of energy in order to work, which is why we have sunlight, and sunlight provides that energy to create our carbohydrates and oxygen. Okay, so once we have these carbohydrates, let's talk about how to classify them. So simple sugars are called monosaccharides. And this comes from the Latin word for sugar. And there are more complex sugars that are made up of multiple monosaccharides. And we would call those either disaccharides if we have 2 sugars attached, or polysaccharides if we have multiple monosaccharides attached together. But we'll discuss those later on. A couple of examples of monosaccharides are glucose, which we just talked about. And we typically draw carbohydrates in Fischer projections. So if you remember way back, we had those Fischer projections. So on glucose, we would draw the following. So notice that we do have 6 carbons. Oops. So we've got 1, 2, 3, 4, 5, 6. We have 6 oxygens, and we have 12 hydrogens. There's another monosaccharide that we can draw, which will look a little bit different. So this monosaccharide is called fructose. Why are these two sugars different? What's the main difference? Well, on the left-hand side, we have an aldehyde at the top for glucose. Fructose, however, has a ketone, so there's 2 carbon groups on either side there. So glucose would be called an aldose because it has that aldehyde group, and fructose could be called a ketose because it has that ketone group at the top. So we can also count the number of carbons in the molecule. So for instance, in glucose, we have 6 carbons. So that would be an aldohexose. And then notice that the ending is OSE. So that indicates that we have a carbohydrate. What would we call fructose? So let's count our carbons. We have 1, 2, 3, 4, 5, 6 as well. So this would be a ketohexose. Okay. So not too bad there. So these are just different ways to classify monosaccharides. If they have an aldehyde, they're an aldose. If they have a ketone, they're a ketose. And then you can further classify them by counting the number of carbons as well. Now let's also look at the stereochemistry here. Now the smallest sugar or carbohydrate is glyceraldehyde. Okay, and there's 2 different ways that we can draw glyceraldehyde. We can draw that OH group in the middle on the right-hand side, or we can draw it on the left-hand side. So the glyceraldehyde molecule on the left, we can label as plus glyceraldehyde. The one on the right we can call minus glyceraldehyde. So remember way back when we talked about enantiomers, we said that enantiomers can rotate plane polarized light in opposite directions, either positive or negative. So these 2 molecules we just drew are enantiomers. So one enantiomer will rotate light clockwise, so dextrorotatory, The other one will rotate light counterclockwise, levorotatory. Now, the dextrorotatory version, so the one on the left, this is more abundant in nature. So let's just make a note. And we're going to refer to this as D-glyceraldehyde. Due to the fact that it rotates light in a clockwise direction. So D stands for dextro. Let's see if I can spell this. Dextro. Oh, rotatory. There we go. That's a tough word to spell. And then the other glyceraldehyde is not really found in nature. It has to be synthesized in a lab, but we can call this L-glyceraldehyde. And L stands for levorotatory. Rotatory. So it rotates light in a counterclockwise fashion. So most carbohydrates are kind of made, for instance, from a starting point. So if we were to make natural carbohydrates, they are all going to come from D-glyceraldehyde, for instance. So D-glyceraldehyde or D carbohydrates are what we find in nature. So sugars are naturally D sugars or D carbohydrates. So OH is on the right. Now remember when we talked about enantiomers, the dextrorotatory and levorotatory directions of light didn't always correspond with the plus or the minus rotation. So not all D sugars rotate light in the same way, but we just refer to any sugar that has OH on the right-hand side as a D sugar, even if it rotates light in a different direction. So just focus on that OH group and whether it's on the right or on the left. So let's practice. Let's figure out if a sugar is D or L. So I'll give you a sugar, and you have to figure out if it is a D sugar or an L sugar. Okay, so I gave you some more carbons here and some more OH groups. So you might be wondering, which OH group do I look at? Well, you're always going to look at the OH group that is just above the last carbon there. So it's always going to be that last OH group on the Fischer projection. So looking at this sugar, would this be a D sugar or an L sugar? Well, the last OH group is on the right, so this is a D sugar. And let's just make a note that we know it's a D sugar because the last OH group in the middle is on the right. So it's the last OH group on a chiral center, I should say. Now let's take this one step further. Is this an aldose or a ketose? An aldose, right? It has an aldehyde group. How many carbon atoms do we have? Well, we have 1, 2, 3, 4, 5. So this would be an aldopentose. Okay, now just a little more practice. How many possible structures of an aldopentose can exist? So what I mean by that, we know that the OH group is going to stay on the right because this is a D sugar. But maybe when we're synthesizing this sugar or creating this sugar naturally, maybe these other chiral centers are opposite. So maybe one of those OH groups is on the left, maybe another one's on the right, maybe they're both on the right, both on the left. How many possible scenarios could we have there? How many possible structures? So remember the rule for enantiomers. You can take 2 to the n, where n is the number of stereocenters. So here we have 2 stereocenters that can change. The last one on carbon 4 will just stay the same since it's a D sugar. So we have 2 to the 2. So that means we have 4 possible structures for this aldopentose. And you can do this for other sugars as well. Let's say we had 6 carbons, so maybe we were looking at an aldohexose. All of those OH groups could potentially either be on the right or the left, except for the last one, which would indicate whether it's a D or L sugar. And then we can just figure out how many possible enantiomers we have there, or stereo isomers. Okay, so let's review Fischer projections, because I know it's been a while since we've gone over those. So let's look at our aldopentose again. And let's say all of those OH groups are on the right. Okay, remember when we're drawing Fischer projections, horizontal lines can be drawn as wedges, and vertical lines can be drawn as dashes. So if we redraw this, we can draw a dash for the carbon at the top going to the next carbon, and then we can draw the OH and the H as wedges, so we've got a little bow tie there. I'm going to keep the next bond as just a regular bond, and then we'll just keep going down the chain. And then at the very bottom, we'll draw a wedge to the last carbon. So this can help us figure out if our stereocenters are R or S. So let's assign R or S to all of our stereocenters here in the middle. So feel free to pause the video, figure out if you have an R or S configuration. Also, keep in mind that all of the hydrogens are in wedges, not dashes, so you might have to flip your stereochemistry assignment at the end. So pause the video, and then when you're done, we'll go over it together. Okay, so let's start with the first stereocenter at the top. What would have highest priority out of the groups that are bonded to that carbon? Oxygen. What would have second priority? The carbon above or the carbon below? Well, the carbon above has a double bond to oxygen, so it's technically bonded twice to an oxygen, right? Whereas the carbon below is only bonded to oxygen once. So the carbon above would have second priority, the carbon below would have third, and of course hydrogen is our fourth priority group. So if we draw a circle from 1 to 2 to 3, is that going to the right or the left? The left. So this would be S, but hydrogen is coming out towards us, so we have to actually flip that to R. So the first stereocenter is R. Okay, what about the second stereocenter? Well, oxygen would get highest priority again. And then kind of looking up the chain to the top, again, we have an aldehyde at the top. If we go down, we have, let's see, kind of the same group. And then after that, we have CH2OH. So I'm going to say the group at the top would win. The group at the bottom would have third priority. Hydrogen would have fourth. So again, 1 to 2 to 3. That looks very similar to the first stereocenter, so that would be S. But hydrogen's coming out towards us, so this is actually R. So following that same logic, the aldehyde at the top is always going to win, right? So our last stereocenter will also be R. So they're all R. Okay. Great. Now, before we go, I just wanted to show you a family tree of aldoses. So at the top, we have D-glyceraldehyde, which we saw earlier. And let's say that we start with D-glyceraldehyde, and then we add another chiral center. Remember that chiral center could either have the OH to the right or to the left. So that gives us two different possible structures for the following sugars. Let's say we then add another chiral center. So if we look at 2A here, the next chiral center could either have OH to the right or to the left. And then if we look at 2B, again, we could either have an OH group to the right or to the left. So overall, we have four different structures there for our aldo, let's see, 1, 2, 3, 4, 5, aldopentoses. And that makes sense with what we saw earlier, right? We said we had 2 to the second. So we had 2 stereocenters. So that would be 4 possible structures. Now, if we take all of those a step further and add another chiral center, again, we're increasing our odds here, or not increasing our odds, but increasing the number of structures. So now there's all of these different possibilities. And if we take into account that we have 3 chiral centers on these aldohexoses, that would be 2 to the 3, which is, let's see, 8 possible structures. So 1, 2, 3, 4, 5, 6, 7, 8. Yep, we have 8 possible structures there. So you can also do this for ketoses. You can do it for L sugars as well, although those are typically synthesized in a lab. But once we start adding more carbons or more chiral centers onto our sugar, we have this whole a wide range of different carbohydrates that we can create. So there are a lot of different carbohydrates out there. Now, I'm not going to make you memorize all the different names of the carbohydrates because there are so many, but I just want you to kind of get a feel for the fact that there are a lot of different carbohydrates out there. Okay, so next time we're going to talk about those different structures that we can draw for carbohydrates. So on the first slide, oops, if we go back, remember I showed you that there are two different structures here. So we can draw the open chain configuration or the cyclic structure. So we'll talk about that next time. I'll see you then.